So the good news here is that profile analysis is just MANOVA again. It's just we're going to use MANOVA a little differently, but not really. Just like one small little step. And because, for whatever reason, it's profile analysis, they've, and by they, it's like this amorphous, non-specific they, whoever they are, decided to name the certain tests with specific sort of titles like flatness and parallel profiles and things, but we'll talk about those. But otherwise, it's just, not only did we just cover MANOVA, and it's just more of the same thing, we also covered mixed ANOVAs in 485, and this is also just the same thing as that. So hopefully you have a grasp on mixed ANOVAs, because this is really just more of the same. That'll become even more obvious when we go to the lab and when we go to actually run a profile analysis. The way we're going to do that is to go in and set up a mixed ANOVA. And in 485, when we would go into the mixed ANOVA output and we would delete the first multivariate table, well, we're just not going to delete that table anymore. We're now going to interpret it. All right. So what's profile analysis? It really is just a way of doing a mixed ANOVA with within a multivariate sort of framework. So instead of thinking of if you have time 1, time 2, time 3, time 4 of a mixed ANOVA, instead of thinking of one dV being measured multiple times, we're just going to treat those 4 times as 4 different dVs that are all just having measured on the same scale. And when we do that, we get profile analysis. And we actually can use the sort of MANOVA framework we talked about before, this sort of matrix approach to getting the sum of squares and cross products and all those things in the same way. The only thing, and this is like a nice new word that you may not have heard before. It's like a nice GRE word, commensurate. Commensurate is a word that means that they are on the same scale, that they're measured on the same scale. So if you have a bunch of items that are all Likert items, 1 to 7 Likert scales, then those items are commensurate. They're all measured on the same scale. And as long as the scales are commensurate, then you can do a profile analysis. So whether or not they're different items or the same item measured multiple times, doesn't make a difference. They're commensurate. You can actually apply this idea of profile analysis to it. All right. The most common use is this repeated measures or mixed ANOVA approach, where you have a set of dVs that, it's really just the same dV, but measured at multiple time points. And that would make them commensurate because it's the same dV on the same scale, just measured at different times. Using this way, it's the multivariate alternative of repeated measures, or a mixed ANOVA. And the choice between whether or not you would do, a mixed ANOVA versus a profile analysis will depend on a couple of things. Likely your sample size. If your sample size is on the larger end, again, vaguely larger end, then it probably doesn't matter. If you have smaller sample, it's probably not going to have enough power to do a multivariate test. And the biggest reason is the assumptions associated with the within subjects ANOVA, specifically the sphericity test. And you probably don't remember, but if you're able to go back, a semester when we were talking about mixed ANOVA, I mentioned at that point that if you violate sphericity, here's a few things you can do. One is to use those adjusted tests, like the greenhouse geyser, Windfeld, those things. You can use more strict alphas, or you can switch to a profile analysis, because that's another alternative. And I think I even said at that point, we'll talk about that in 524. Well, that day is now, and we're talking about that thing. There's another alternative. There's a trade-off. Profile analysis has slightly less power, but it's got the assumptions are easier to meet relatively. Sphericity, like I mentioned before, is really, really difficult to meet often. This is going to be violated more often than you're going to meet it. And one alternative is just to interpret the multivariate test instead of the univariate ones. So this is, I just realized I wore a shirt that almost matches the the color scheme I chose for the slides. Well, this is the basic setup for this, right? You got, if this were a mixed ANOVA, you got two groups, which is the between groups part, and then the same DV measured at time 1, time 2, time 3, time 4. That's the basic setup. We're calling this, and this in this context, we're calling it a profile analysis, but last semester we called it a mixed ANOVA. The data setup is the same. Everything you pretty much would do to it is the same. It's just we're going to interpret different parts of the output. All right. The less common use is to compare groups on different DVs that happen to be measured on the same scale, like subscales from the same inventory. Let's say, I don't know, you want to look at the pattern of scores across subscales of the MMPI, and I don't even know the MMPI that well to know if the subscales are on the same scale. But let's assume for a second, for the sake of argument, that they are. And if they're on the same scale, then you can actually use profile analysis to compare folks on different DVs that just happen to be on the same scale across two groups. And that's really where the name sort of profile analysis comes from. You actually want to know, are these different groups, do they have the same profile across the repeated measures or commensurate DVs? And if you've ever seen the MMPI or looked at how it's sort of scored, it often is you're often given a profile on the subscales that you're high and low on, and the combinations of those often can help psychologists and other folks sort of diagnose different disorders. So the profile as a whole matters, not any individual subscale. So profile analysis actually sort of does that sort of thing. Are different groups, do they have different profiles across multiple DVs? All right. Current stat packages can be used to perform more complex analyses where there are multiple factorial between subject effects. This is what I mentioned in the last, sort of the end of the last lecture, that one of the things that I left out, I took out of this lecture to sort of, to cut some things out, is at the very end in your slides that you have off of GitHub, there is a section on doubly MANOVA. Doubly MANOVA really just, this actually says multiple factorial between subject effects. Let me back up a second. So in a mixed design, you could have factorial design here where you have, say, men and women at treatment and control. So it's sort of factorial between groups, and still just have one repeated measures DV. With doubly MANOVA, you actually have a factorial design on the repeated measures part. So like I said here, imagine combining those two things together. So you have for the commensurate data, you have two groups, and you have 4 different DVs, and that's basically a profile analysis using commensurate data. But now, let's say I had these 4 DVs measured at time 1, and then I had the same 4 measured at time 2, the same 4 measured at time 3, and that essentially, when you have a factorial repeated measures component, that is a doubly MANOVA. You can do anything you want on the between subject side. So going back to like the repeated measures part, this can be as factorial. I can have 7 IVs that are between groups, 1 repeated measures component, and that's essentially just, it's still a profile analysis. It doesn't change. The doubly part comes when you actually have commensurate data measured at multiple times, that now it's basically a double profile analysis, but instead of calling it a double profile analysis, they call it doubly MANOVA. The idea is that the between groups part can have any amount of layers in it. You can have as many between groups IVs as you want, and it's still going to be just a profile analysis. But as soon as you add another layer on the repeated measures part, it becomes a doubly MANOVA, which we're not going to talk about specifically in here. I think even in lab, there's a doubly MANOVA part. We're going to skip that too. It's something, if you really want to, you can come back to later. I don't see a lot of people actually doing it because it gets rather complex, but if you do, the good news is there is a section in the Tabashka and Fidel book that covers it, like sort of how to do it and how to analyze it, and it's in the notes. I'm just not going to cover it because of time. Anyway, said that. Okay, so what are the questions? the question, so back up a second. There's two main uses. One, same DV measured multiple times, or multiple DVs that are on the same scale. Those are the two main applications for profile analysis. You got to have at least two groups, between groups, and then some kind of repeated measures part. Right, so it's got to be a mixed ANOVA design to some degree. So what are the questions that we ask? What are the main things? So spoiler, they're the same as they are in a mixed ANOVA. We're going to look for main effects of the between groups, the main effect of the within groups, or the repeated measures, and interaction. It's just for whatever reason, in profile analysis, they've named those tests, right? So instead of just saying, oh, it's a main effect for groups, they actually gave it a name. So, and each test in profile analysis, they're named after the null states. So that's also confusing. So we'll come back to it in a second, but if you're looking at if you're trying to test the between groups effect, the actual between groups, not the repeated measure, but between groups effect, that effect is called equal levels. Well, if you have equal levels, it means you're not going to reject the null hypothesis, right? You're actually going to retain it. The groups are equal. So the whole point is you're trying to reject the equal levels hypothesis. So it's called equal levels, but that's what you're actually trying to reject. Same thing with flatness is the repeated measures one, you're trying to reject it. And parallel profiles is the interaction one. And again, you're also trying to reject that. And if you're doing this, you probably don't think the profiles are parallel, and that's actually why you're doing a profile analysis in the first place. So again, they're all named after the null case, which at some point, when you're trying to do this, this is going to confuse you. Because you're like, oh, the equal levels test is significant. Wait, crap, does that mean that they're equal, right? So just remember that it's always the null case is what they're named after, and typically you're trying to reject that null case with your hypothesis. So what's the one? I said that this is basically just MANOVA with just one difference, one additional thing. The additional thing is that we're going to create something. And again, they have to name everything. You're going to make everything jargony. We can't just call them difference scores. We can't just call them something simple. What do they call it? They actually call it segments. Right? So what are segments? Segments are, in doing a profile analysis, because it's the same DV over time or different DVs on the same scale, that gives us an advantage that we don't have in regular MANOVA. So with MANOVA, we don't have that assumption. We can have DVs measured on any scale. It doesn't make a difference. We're going to just try to combine and make groups different. All right. With profile analysis, because the DVs are scored on the same scale, we can treat them differently. Right? We can actually subtract them. So if I have the same DV measured multiple times, there's no reason why I can't subtract, say, time 1 from time 2 and time 2 from time 3. I can actually subtract them because they're on the same scale. That kind of difference score actually makes sense when they're on the same scale. If you're doing a regular MANOVA and the DVs are all in wildly different scales, subtracting them doesn't make any sense. It's not really something you can do, or at least, I mean, I guess you could do it, but it'd be weird. So at least here, because the scores are meaningfully the same, we can subtract them. There's actually different other kinds of linear combinations that you can do, but typically what they do is they take adjacent DVs, like time 1 and time 2, time 2, time 3, and they subtract them. What that does is creates different scores. So instead of having 4 individual time points, let's say if you had 4, time 1, time 2, time 3, time 4, you're going to end up with 3 segments. Each of those represents the difference between adjacent time points. Okay. So we'll come back to what that means in a second. I'll show you an example. But that's what we're going to do is we're going to turn all the DVs into segments, basically subtracting adjacent scores. And then we're going to run a MANOVA on the data with the repeated measures parts in segments. Why they call them segments? No idea. It doesn't even make any sense to me that they're called segments. It's not like they're cutting it into pieces. They're actually just, I don't know. A segment is a weird term to me for what this is, but that's what they call them. That's sort of the term that gets used to describe the initial step in doing a profile analysis, subtracting scores and creating segments. Each of the differences now are called segments. Don't know why. It wasn't me. Don't blame me. So, all right. So the questions that we're going to be asking, basically, again, we're going to get 2 main effects, 1 interaction. So the first main effect is strangely univariate. Okay, so we're not even going to do for the equal levels test. Okay, so equal levels, again, that's the null case. So it's that the between groups that you have, whether it's 2 or 10 or whatever, that they all basically have the same mean, that all the groups are at the same level. They're equal levels. So on average, there's one group score higher than the other. So by on average, it means averaging across all the DVs. So if I take time 1, time 2, time 3, time 4, and I average across them, I'm going to get a mean for every single person, and then I can actually do basically a one-way ANOVA, a univariate one-way ANOVA, comparing those scores to test for equal levels. This would be the between groups main effect in a mixed ANOVA. As a matter of fact, we're going to interpret the exact same between groups main effect, like the univariate effect that was in the mixed ANOVA in the first place. So this one's going to be treated univariately. All right. So something like this would be sort of an equal levels test. So even though across time, so hopefully you can see there's a group 1 and group 2 is like a dark like blue, and the other one's like purple or pink or something. That they're, even though at time 1 to time 2 they're increasing, and then they're decreasing again at time 3 and increasing again at time 4. Both groups are at the exact same level. If I were to take and average the 4 points across time, if I was to sit and sort of collapse this together all the way over, I would get an average that's probably somewhere about here, right? So the average of all 4 points would be about here, and both groups would be at the exact same point. So even though there's a lot of stuff going on, we would not find a between subjects main effect here. So you probably thought that BS meant something else, but it's that's for between subjects. There's no between groups, no between subjects main effect here. So this again is the null case. If equal levels is met, meaning you don't reject equal levels, you would find something like this, where both groups across time are at about the same level. Are you with me so far? So like we'll see in a second, there's another test called flatness, which sounds exactly like it is. We're testing to see if we were to collapse the groups together, right, so collapse this way, they're basically already collapsed, would the means create a flat line? Right? Well, in this case, we would actually reject flatness. Even though we would retain equal levels here, we would reject flatness. And we would also keep parallel profiles, which we'll get to in a second, because both groups have the exact same profile with one another. All right. So the second main effect is something called flatness. It's a test for flatness. And again, this flatness is what we want to reject. If we think there's actually differences, that groups are different across time, we're actually looking to find a flatness test. To reject the flatness test. Anyway, so this is the within subjects component that we're actually going to test multivariately. So we're going to look at that first multivariate test table that you get at the beginning of a mixed ANOVA, and we're going to interpret those values. So basically do all the DVs elicit the same average response. Again, this is ignoring groups and just trying to see if we're getting the same average, if we average across groups this time. We get the same average across time for all the DVs, or across time, or for each across the DVs if they're different commensurate DVs. This is usually only tested if parallel profiles is not rejected. What the hell does that mean? This goes back to the idea that if you find a significant interaction, then really any main effect that you try to interpret in the context of a significant interaction is probably difficult, because if it's sort of saying, if you're looking at like math ability, across time, and it's so, boys versus girls or something like that, and you have an interaction, you're basically saying, all right, the change in math ability over time depends on whether you're looking at boys or girls, where boys start higher, change slower, girls start lower, change faster. All right, so it's an interaction. And if someone says, okay, well, who's better, boys or girls? You're like, well, I just said it depends on, like, there's a difference across time, but you're like, oh, I don't care about that. Just on average, who's better, boys or girls? You're like, well, I just said it depended on, right? So to try to interpret any main effect becomes complicated when you have an interaction, because the interaction is supposed to give you context and say, hey, you can't generalize any of the main effects because the interaction is significant. So it's the same thing here, that if, say, parallel profiles is rejected, which is our interaction test, then we probably shouldn't really be interpreting the main effect for the test for flatness, or even the equal levels test. But we'll talk about that more in a second. All right. So this looks like this. If we to look at the type of profile where you would get a null case here. So if you look at the two groups, group 1 and group 2, they have very different patterns. Actually, they're like a mirror image of one another, where both groups start about the same place, but they move apart from each other, come back together, and then move apart again. But if I were to take each of the points each time and average them, I would get an average about here, about there again, and about there again. Those averages, averaging across the groups this way, would result in a straight, flat line across the board here. So that means that we would not reject flatness. This actually means that we should retain this null version. We should actually, well, flatness seems like a pretty good explanation for this, so we're not going to reject it. So this is the null case for the repeated measures part. Okay. So really the reason people typically do profile analysis, like the main motivation, is because they think they have groups that are going to differ across time. So basically we're looking at the main goal is the interaction. Interaction is the thing that's of most interest. So are the profiles for each, or the 2, 3, 4, 10 groups, whatever you have, are those profiles roughly the same? This is a test for the interaction in a repeated measures ANOVA, right? It's the same thing. It's basically the testing for the interaction. It's just now we're going to do that multivariately, and they can be done on the segments instead of on the actual DV scores. Like I said here, this is the main reason, the main motivation. Why would I want to do a profile analysis? Well, because I think I have two groups. One's getting intervention and one's not. I think the intervention group is going to go down over time, right? Where the control group is going to stay the same, be flat. They're going to have two different profiles. That's the main reason I'm trying to use, or that I want to use this test in the first place. So an interaction occurs when the profiles are not parallel. So again, an interaction means that we're rejecting the parallel profiles hypothesis. Again, a parallel profiles is the null case, and we typically want to reject that case. And we're not trying to keep it. Questions so far? Actually, I should probably show you this, and then we'll talk about questions. So if you look at these two groups, we can see, so it says up here, no interaction. So here we'd actually get we would actually retain the parallel profiles case, because the patterns of the means across time are exactly the same. Which hypotheses would we reject? There's two others, so which other ones would we reject? We would reject flatness, because if you were to average across the groups, right? If I average, this average gives me a point here. This average would give me a point somewhere up here, right? And so you get this sort of the same zigzag pattern would occur for if we actually average over groups. So it definitely would not be flat. What else would we reject? Exactly. So if I average all the points on the pink line, I'm going to get some point somewhere around here. If average all the points in the blue line, and we get some point around here, those are likely to be different. Obviously, you'd have to test it. You know, I'm claiming, oh, it'd be significant. I mean, I don't know if it would be, but it's likely, you know, that those would be rejected, while the parallel profiles would not. So even though the profiles, I almost said, even though the parallels are profile, anyway, even though the profiles are parallel, we still, in this case, this is where the main effects actually become more meaningful, right? Because the interaction is not significant, so there's no contingencies. I don't have to say, well, the pattern of across time depends on the group. It doesn't. It's the same pattern, right? The pattern's the same. So all we know is, well, which group did better, right? Well, the group 2 did better. They had higher score, or assuming that higher scores are better. Maybe that's worse. I don't know. But you know, the group 2 has higher scores, so we can interpret that just fine. Across time, we know for some reason, time 1 to time 2, scores increase. Time 2 to time 3, they decrease, and time 3 to time 4, they increase again. What do you think would make that pattern? This pattern where groups get better, and then they get worse, and then they get better. What kind of scenario would you see something like that in? That would just be like, no. Anyway, but no, I mean, during the pandemic, they would get better than worse, and I mean, so let's use the pandemic as a thing. So let's say we had 4 exams in class, and I randomly assigned the class into 2 groups, or we can even just make it easy. Let's say it's like, not to be stereotypical, but like, you know, pink line for girls, blue line for boys. We got like the males and females in class. I wanted to see if there's a difference across time. So let's say we're going, the beginning of the semester, everything's going fine, you know, but you know, the first test is always hard, so it's a little bit lower. Class goes forward, we get to the second midterm, and everyone's scores are doing better. The pandemic happens, we're now at the stay-at-home order, people's scores start to go back down again because it's hard to study or whatever. We adjust to the pandemic, or let's say the pandemic ends and things go back to normal, and the scores sort of increase again. So there's lots of types of studies where they'll do like intervention, and it's called like an intervention reversal or dose. What's it called again? There's actually a name, but it's basically where you give so let's say from time 1 to time 2, you give an intervention. So someone starts taking a drug, right? They get better. Then, without them knowing it, you give them a placebo. They get worse. You switch them back to the drug again, and they get better again. So this actually is a way of verifying that it's the drug itself, not the placebo effect, right? So they get the actual drug in between time 1 and time 2. Between time 2 and time 3, they're given a placebo, and then in between time 3 and time 4, they're given the drug again to see that it actually reverses. It's a regression reversal, or I forget what it's called. There's a term for when you actually will change the intervention, and you give an intervention, take it away, and then give it again to see that it actually reverses the trend of the line. Because if you switch them to placebo and they just continue to get better, right, then the drug's probably not doing a whole lot. Questions about equal levels, flatness, parallel profiles? So yeah, it's if these, instead of thinking of them as time 1, time 2, time 3, time 4, if this was like dv1, dv2, these are just different dv's measured on different scales, doesn't matter, right? Then we would run this as a MANOVA. We can actually plot these things out. It becomes a lot less interesting because in a MANOVA there wouldn't be there's no main effect as an interactions. Right? It's just, these are 4 different DVs, all these groups different. Is there a way to make those groups different by combining these together? If there is, great, it's just one effect. this is now sort of using the same methods to sort of extend it out a little bit and actually get tests for both interactions and stuff, because at a minimum you have to have at least a factorial design, not factorial, but a mixed ANOVA design. Here, Lone, I can pick on you, because so describe really simply that Parents Anonymous study that we're doing. I'll have to repeat it because then we can hear, you won't be able to hear it on the thing, but tell me the basic design of that study. Let's just focus on one of the outcomes. Okay. And then what are our groups? Right. So I think group 1 is that it's like they have to have like 11 or more or something like that attendance, and group 2 or something. What the hell am I writing? Group 2 is they're like 10, or they're less than 10, or 10 less than equal to 10, or something like that. So the idea being that it's about the same amount of time. Most of the time between time 1 and time 2, it's often about 3 months or something like that. And in that 3 months, you got people that actually come all the time. They come every week. They're very regularly attending. Parents Anonymous, I should state, is it's basically like an intervention for parents of any type that just want help. They want like a social support network. They want other people who have kids or having issues. They want to be able to have like a group they can go and talk to. There is some cases where parents are mandated to go to it. So like DCFS is getting involved, and they're at risk of losing their kids to foster care or something like that. They may recommend that the parents go to Parents Anonymous to help with parenting skills and hopefully improve, and then their kids then don't get put into the system. So anyway, so you got about the same amount of time. You got sort of high attenders and low attenders. I'm trying to figure out, is there a difference, and what's one of the outcomes that we were looking at? Okay, so parental resilience. So what tends to happen is that, at least when we're looking at the whole thing, is that the group 2, group 1 is the sort of high attenders. They actually tend to be the ones who, again, parental resilience, the higher the score, the better. They tend to be the ones who actually start off with lower parental resilience. So I'll just call this PR for parental resilience, okay? So they start off lower. I don't remember what the scale is, but okay, so let's say here they got 7 and they got 1. So they tend to start off lower. If you're looking at time 1, where the group 2 tends to, actually use a different marker, they tend to start off a little higher because it's almost like the motivation to attend a lot is that they don't have the thing when they start off. So what you get is, across time, these folks may get a little bit better, but not better as fast as often the other parents do who attend more often because they need it more. Okay, so in this case, we know right away, because of this, we would actually reject the parallel profiles. Their profiles are not parallel. This is a very simple, with only 2 time points, but again, there's an interaction, so it's likely we wouldn't reject the parallel profiles. I'm sorry, that we would reject the parallel profiles test. What else? Would we reject the equal levels test? Are the groups different overall? Think about averaging, somewhere there and somewhere here are the 2 means. They're a little different, probably not a whole lot different. All right, so unlikely we reject the equal levels test. Right? The groups are not super different. What about flatness? Flatness? No, because yeah. So for equal levels, I'm averaging over time, right? So I'm getting, let me do it this way. Equal levels really looks at, is this line, right, different than that line on average, right? We're getting, right, there's a small difference between the two of them. I'm just extending out the x's out here, right? So looking at these two averages, where with I want to average across the groups for each time now. So I'd have one average there and one average up here. So this is what the sort of flatness test is testing. All right, so they change, both groups change. So in regular language, forget about the parallel profiles, equal levels, blah, blah, blah. Do people change across time in general? Well, yeah, it looks like it. Everyone who goes to Parents Anonymous is getting better. Time 2. All right, so that's that test. Is there a change across time? Are people getting better? That's the flatness test. If they weren't getting better, the line would be flat. Right? We get the same, the same thing on both time 1 and time 2. No one's really changing. So the flatness test is looking at the effect across time. Now, if you ask the question, which group did better, the high attenders or the low attenders, you can say, well, the high attenders did a little better than the low. The low attenders overall did a little better than the high attenders, but that may not be significant. All right, the blue line, I should probably label them. Blue is group 1, group 2. Yeah, and this is group 1. Okay, so overall, group 2 did a little better than group 1, but it's probably not significant. And then the question is, well, all right, did the change across time differ for the two groups? And if we put that into English, right? Well, for group 1, they started off worse, but they changed more. They actually got more out of Parents Anonymous. They changed more from time 1 to time 2. Group 2, they started off a little better, but Parents Anonymous didn't help them as much. It's like because they didn't attend as much, so they didn't get as much out of the intervention. So that's really getting at the parallel profiles. So when you're asking about interaction, well, does the change across time depend on the group? Well, the answer is yes. Group 1 tended to change faster, and the group 2 changed slower. If the question is which group is better, that's an equal levels test. In this case, group 2 is better than group 1, but not by very much. And then if the question is, all right, well, did the intervention work? All right, forgetting about who does Parents Anonymous work across time? That's looking at the flatness test, and the X is, well, everyone that sort of came got better. So there does seem to be some evidence that Parents Anonymous is sort of working to improve people's scores. It just works better for people who attend more than who attend less. But that's somewhat misleading, because it could be that the people that actually attend more, it's because they need it more. They're more motivated. People who attend less don't need it as much. They don't come as much. That's why they don't get as much out of it. This could also be sort of a regression to the mean situation, where if you find people at the worst time, right? So they're having some crisis, their kids are about to be taken away, there's all kinds of other issues going on. They're going to be more motivated to change and sort of adjust back to where they sort of probably were before the crisis happened, right? So there's a lot of things going on that sort of confound the effects, but breaking it down in this way, at least we know the equal levels test, the flatness test, which is that pink line, and then there is some, looks like rejection of parallel profiles. Okay, does that help? Yeah, I mean, there is a difference. I'm just assuming the difference is probably really small because the lines are, they're basically crossing. So the mean up on this side is actually pulling this mean up closer to where the blue line is. It's possible if you had a large sample size that this difference for equal levels would also be significant, but without doing a test, we wouldn't know. Of all of them, I would guess that's probably the one that wouldn't be significant, while flatness probably would be, and parallel profiles likely wouldn't be. And the reason why we started doing this test in this way with parents anonymous was because we actually want to show this idea of parallel profiles. So this intervention, they don't have controls. Anybody that comes parents anonymous, they get to do it, right? So they don't have like a wait list. They don't have anything. It's oftentimes parents in sort of crisis around their kids, so they're not going to be like, okay, I know your kid's about to be taken away by DCFS. Come back in 3 months and we'll help you. So anybody who shows up gets sort of treatment. So they don't really have a control group. So the reason why we looked at attendance was this is sort of ad hoc sort of control group where people had sort of low attendance. Again, they're supposed to come about once a week. And so within pre and post time, they should have 20 or more sort of times that they've attended. Was that right? That's not right. Or they should have closer, they should at least have 12 or something more. I guess you can come more than once a week. So I'm trying to think, it was like 3 months in between. And they come once a week. That's really 4 weeks. 4 weeks. 4 weeks is about 12 times. So I guess they can come more often. Anyway, it doesn't matter. I'm like just thinking off the top of my head. But we actually created this sort of ad hoc group to show, okay, well, they're getting less of a dosage of the thing, so the effect should be lower. And I found some interesting things about that there actually is some prediction that if you're coming less often, it's likely because you started off in better shape to begin with, so you didn't need the intervention as much. Or it's possible that you came and realized you didn't need as much, and that's why your attendance sort of leveled out or stopped altogether. All right. Any other questions? Okay. So just like with anything, think about your mixed ANOVAs. Anytime you have main effects, interactions that are significant, there are always going to be follow-up tests, right? So if any of the hypotheses tested by profile analysis are significant, so you've rejected flatness, you've rejected equal levels, you've rejected parallel profiles, right? You're going to follow them up with some kind of contrast. Now, assuming that you have more than, like with any main effect, you have to have more than 2 times or more than 2 levels or 2 groups in order to need a follow-up test. But assuming you do, you're going to look at things like simple effects for the interaction, right? You're going to look at simple contrasts depending on which one, there's a whole thing where if the interaction is, I gotta think about this for a second, not both. Yeah, simple effects and simple contrast are going to be the 2 follow-ups. Do I actually have it on the next slide? I don't. So let's say you have an interaction significant. One of the main effects is significant, but the other one is not. So you can actually cut it up into pieces based on the main effect that's significant, and do a simple effect, which is, this is the other name for simple effect is, so basically they call it a simple ANOVA. Okay. And then if the simple ANOVA is significant, you're going to do then the simple contrast if this is significant. So as a reminder, because I'm sure you didn't have this memorized from, let's say you have, from 45, let's say you have 3 time points, time 1, time 2, time 3, and you have group 1, group 2, group 3. And you find out that the interaction is significant, and you want to be able to break it down. Crap, hold on. Just realized I drew it. Here, I can do this. I think. Let's see if this will work. Yay. Look at that. So let's say you have 3 time points, 3 groups, and the interaction is significant, and let's say the groups, let's say this is significant, but this is not, meaning that flatness wasn't rejected, but equal levels was. There's also an interaction, so there's a parallel profiles rejection there too. So what is a simple ANOVA, or a simple effect? So simple ANOVA means I'm going to take and let's see, I'll use yellow. I'm going to grab all 3 groups at time 1, and I'm going to do just a simple analysis of variance comparing those 3 groups, 2, 3, all at just time 1. That's a simple ANOVA. And do the same thing for the second one. Pull these apart. And I'm going to do the same thing for this one and pull them apart. Right? So this is time 2, this is time 3, and I'll compare those groups doing separate ANOVAs for each one. Let's say this one is not significant. This one's not significant, but this one is. Well, now I need to then do, comparisons of each group, like do these 2 cells versus one another in like a t-test. And this would be a simple contrast. All right, we're following up a simple ANOVA or simple effect with comparisons of each group so that I can actually find out exactly what's driving the significant effect. So what's driving the interaction? Well, there's no difference at time 1, no difference at time 2, but there is a difference at time 3. So that's what's driving the interaction. Okay, well, which groups are different at time 3? Well, now I need to find out by doing this sort of simple contrast to figure that out. So it goes, the overall effect. This was the same as it was in a mixed ANOVA. You do the overall factorial, or mixed ANOVA, and then if there's some effect, if there's a main effect that's significant and the interaction is significant, you can break them down using simple effects and simple contrasts. And we can do the same thing in a profile analysis as well. Questions about that? So, remember I said here, interaction and possibly one, but not both main effects. You're going to do simple effects followed by simple contrasts. What if both of them are significant? You have main effects and interaction significant. There's no clear way to sort of break them down. You can do something called interaction contrasts. And we'll talk more about that later on. It's actually ways of breaking down the interaction to smaller interactions. But come back to that. So another question you can ask is sort of, can we estimate parameters for, population values, that kind of thing? Usually done through the plots of the actual profiles. So if flatness is rejected, you're going to plot the average DV scores across groups. So you're going to average out all the DV scores and for each person, and then average those across groups to get, wait, wrong one. Plot average DV scores across groups. Equal levels plot group scores across DVs. Yeah, so I guess the across here doesn't mean not even being consistent with my own language. So flatness rejected, that means that if you were to take an average across the groups, the pattern of means is not flat, whatever that means, up and down, or it's going up, it's going down, whatever it is. So plot average DV scores, and we're going to average across groups. So average across groups, get an average DV score, and then you're going to plot them. For equal levels, you're going to average across the DVs in each group, and get means for each group to compare them, and actually plot them out that way. And for parallel profiles, you're basically going to take and plot a different mean for each group on each DV. So you're actually getting all the means and getting a sort of a pattern. If you're thinking about it as a mixed ANOVA sense, one mean per cell, combination of group and time, or group and DV, to get means for each combination and plot those out. So the same way we did, back here. This is basically plotting out for parallel profiles. This, even though this is really, it's saying flatness, the plot actually is plotting out parallel profiles because you're getting one mean for each group at each time. So this kind of setup is good for doing parallel profiles plotting. But if I wanted to look at flatness, I would just plot the dotted line. If I wanted to look at just equal levels, I would just plot group 1, and forget about the time now. I'll just plot group 1 and group 2 and show that they have different means. So I'm averaging over time and just plotting, having one mean per group and plotting that. This is a way of sort of looking at what the parameter estimates might be for the population. So that's why it says, so plot average DV scores averaging across groups, equal levels, plot groups scores averaging across DVs, and for parallel profiles, you're basically not going to average across either the groups or the DVs. You're going to get one mean per combination of group and time, or group and DV, and plot those out to look at the interaction. And then there's, measures of strength of association like eta squared and partial eta squared. Those are essentially going to be computed the same, especially when you think about it in terms of MANOVA. We can calculate multivariate versions of this and the univariate versions, and it's the same process. So I'm not going to go into a whole lot of detail about it, but it's the same as it was, sort of combining together mixed ANOVAs from before, where something like equal levels, because it's univariate, you can compute just a simple eta squared or partial eta squared. For flatness and parallel profiles, because they're multivariate, you can get a multivariate version of those using lambda or something, and but also do the univariate versions of those when they get sort of broken down into univariate components. All right. So there's not a whole lot of limitations with profile analysis relative to MANOVA. It has one limitation, or one extra assumption, or whatever you want, however you want to call it. Data must be on the same scale. So I've seen people try to sort of fit a square peg in a round hole. They don't have, they don't have commensurate data, so they try to force the data to be commensurate. So they'll take z-scores and to try to make the data, commensurate, being all on a standardized scale. The problem there, though, is you're also subtracting out the means from each one, so you're automatically going to flatten everything out, which is a problem. So if you're interested in looking at, rejection of a flatness hypothesis, you're likely not going to find it. And each of the different DVs at different times may have a different standard deviation. So if you're going to standardize all the scores to one standard, it should be done using like a pool within subject standard deviation, and not just the ones within each of the time points. You can also use factor scores, which we'll come back to, meaning that you have a bunch of DVs that are measuring something similar. You could use those to create a factor and create factor scores for each person instead of using all the DVs combined, as a way of sort of getting around the commensurate data issue. And there's, all this stuff sort of gets problematic because we're dealing all with sample estimates of population standard deviation. So nothing's, the more you try to estimate, the more you're trying to get a good estimate of the population value, the more likely you're going to fail at it and not really get to a point where you want. So even though, so for instance, if I'm using this pool of standard deviation to try to standardize everything to make them commensurate, well, that may not actually reflect the population value well, and what you're going to get is not going to be very reflective of the population in terms of change over time, or parallel profiles and things. All right. And these are the same limitations that we have for every analysis, which is any kind of causality, to say that the differences in groups are causing a change over time. that's actually limited to manipulated grouping variables, grouping IVs. So if you're doing something that's experimental, where you're able to manipulate the variable, then you might actually get to talk about causal effects. Otherwise, you're not talking about cause. At best, you're talking about prediction or correlation. And be real careful where you're generalizing. Don't overgeneralize to populations that you didn't even include in your sample. So make sure that your generalizability is limited to the population you used, that you sampled from. Oftentimes, if you actually were to sit down and ask somebody what population of people that they're trying to target with their study, they either won't know or they'll be grossly off of what they actually think they're doing. So you got a lot of people will be like, "Oh, I'm interested in looking at mental health in adults." Okay, so your population is what? Okay, well it's adults ages whatever 18 to 65, living in California. Okay, well, where'd you sample? Well, I use a subject pool. So your sample from your population came from just undergraduate students taking 150 who are probably 18, maybe to 22, and you think that reflects the population of people going from 18 to 65 living in all of California. Yeah. Okay. Whatever you say. So make sure that if this is sort of outside of this class. This is more like 692 or even a 321 question. How do you go about sampling from a population and make sure that population gets included? But also, even before that, even before the sampling part, how do you define what your population is, or who that includes, and how do you sort of put some sort of parameters around who is in that population to make sure that they get included when you're actually doing the sampling? And if that's not possible, you need to narrow down the definition of who your population is and who you can generalize to. And oftentimes people don't really think about this very much. And when it comes, they're so focused on wanting to get a significant effect, they forget that they're actually trying to infer it back to a greater population, that it never actually even happens. Anyway, that's some soapboxing from me. Anyway, I see that quite often. People just like, oh, it's significant. All right, cool. What does that mean? How does that actually impact the population you're interested in stuff? And they often don't really know. It's really hard for them to connect the two together. And then I'm not sure there's really a limitation, but we're going to talk about sort of assumptions. And as we talk about assumptions, we have to think about the assumptions that are being tested on combined DVs, but often difficult. That's often difficult to do. So often you'll see people say, oh, we need to look at multivariate normality, or we need to look at things that are sort of across multiple DVs together. But sometimes there just isn't those tests just aren't readily available. So they often revert back to using just each individual DV and testing the assumptions there. And there's then another layer of an assumption, which is, well, if it's fine at the univariate level, then hopefully combined, it's all fine as well in terms of multivariate. But it's not always the case, but at least it's better than doing no testing whatsoever, and no assumption checking whatsoever. So as you probably guessed, I really could, like with the assumptions, could sort of skip it and say, look, they're the same as they are from ANOVA. If you think about the assumptions in a MANOVA and combined a little bit with assumptions from mixed ANOVA, we pretty much cover everything. They got to be commensurate, should be normal, no outliers. In the equal levels test, because it's univariate, you want to assume homogeneity of variance. For the multivariate test, you want to assume the homogeneity of variance-covariance matrices. So it's sort of, there are different assumptions that apply to different aspects of the design because they're being tested different ways. Some univariate, at least one univariate, and some multivariate. So we're assuming that, like with sample size, we're assuming that it needs to be large enough so that you have enough power. You need more subjects in the smallest cell, the number of DVs. That was the same thing we said for MANOVA. The same thing applies here. This affects the power, and it's going to affect the test for homogeneity of covariance matrices. in the same way you did for MANOVA that we talked about in the last set of slides. So because it's really just an application of MANOVA, all the assumptions are essentially the same. And make sure here the sample size data can be imputed because you have more scores coming from each individual person. The chance of them having one being missing a score or scores is higher. Instead of throwing that person out completely and doing a complete cases analysis, it's now a good time to utilize the missing value analysis in SPSS, for instance, do multiple imputation, and retain as many people as you can using those methods. Power is determined in a couple different ways. So looking at profile analysis by itself, right, it's lower power than the univariate test. We talked about that with the keys example in MANOVA. Same thing happens here. But there's a little bit more of a decision tree here. So you could decide to do a mixed ANOVA. So your plan is, I'm going to do a mixed ANOVA. And as I start to do the mixed ANOVA, I get back that sphericity is violated. So with Mockley's test of sphericity comes back significant in SPSS. So you now have a choice. You can either try to do the corrections, Winfeld, Greenhouse Geyser, those things, or at that point you can switch to a profile analysis which has slightly less power, but the assumption of equality of covariance matrices is easier to meet than sphericity is. So it's often you have more power switching to profile analysis than you would trying to take one of the corrections, because the corrections actually are often very conservative and they do a lot of correction, which may mean it can totally kill the power of your study. So now this is now a new sort of tool in your toolbox of analyses that if you do a mixed ANOVA and you run into the problem of sphericity, well, all you got to do is switch to interpreting the multivariate table instead of the univariate one. And that's a way to address the issue and avoid the significant sphericity test. We're assuming, just like with MANOVA, multivariate normality, right? So there are more subjects in the smallest cell than the number of DVs and relatively equal n, then profile analysis is robust. This is the same assumption as was for MANOVA. If your analysis, your data set is essentially balanced, meaning that the cells in the design are roughly equal, and you have more people in the smallest cell than DVs, you can probably ignore the multivariate normality sort of testing anyway. And you probably could skip testing it altogether. But if very small samples and unequal n, then you need to look at the DVs to see if there's skewness univariately, and there's some ways of graphing them multivariately to see too, but it would go outside of SPSS. But you might be able to do some multivariate normality graphing and see if there's sort of combinations of things that are causing issues. Other programs, when you get to things like structural equation modeling and stuff, they actually do test for multivariate normality and will tell you if it's violated sort of as part of the output without even asking for it. Outliers, you don't want them, so check and make sure there aren't any. Again, that's distributional outliers, like people that don't seem to fit, their responses don't seem to fit in the distribution, but also just even sort of theoretical ones too. Or population-based ones. There's people that you're targeting, somehow you got people that weren't supposed to be in there. Those are also outliers. They should also be removed. Univariate outliers you can fix, you can rein them in, you could delete them, whatever. Multivariate outliers are tougher. So look at things like oh man, I'm blanking out. Mahalanobis distance. Man, I couldn't think of the word Mahalanobis for a second. Mahalanobis distance and to see if there's any multivariate outliers and stuff. You can't really fix those. Like there's no reining those in or changing the scores to make them less multivariate outliers. But at least you can identify them and remove them. And if you do decide with any outliers to remove them, I recommend running your analysis with them in, have them flagged, remove them, run the analysis again, and if the analysis does not change very much, you're getting the same results, it's likely you can just sort of leave them in. Because it's harder sometimes to justify removing people than it is just to leave them in if they have no impact on the outcome. People get suspicious when you start dropping people out, like you're trying to manipulate your data to sort of get what you want. So sometimes it's easier to avoid doing that if you have to, or if you can. I mean, what time is it right now? 10:45. All right. Let me see. Linearity. I mean, all this stuff. Look, homozygous covariance matrices, same as it was in MANOVA. Linearity, same as it was in MANOVA. We're assuming everything's sort of linearly related. This really just is repeating stuff from MANOVA. It's nothing all that different. It's just sort of wash, repeat with profile analysis. So we'll start on Tuesday with the equations. Again, they're mostly the same. I'm not even going to go into as much detail with them as I did with MANOVA. All we're going to talk about is the first step of making segments, and then how do you go through and sort of apply the MANOVA process using the segments. And that's really it. It doesn't get nearly as technical as the last one.